Okay. I think we're back. Wow. That was crazy. That was a crazy moment then. So yeah, welcome everyone. And what happened to my music?
Come on, come here, bud. Come on. You freaky dog.
Oh boy, have I had a bad few moments? So that whole stream went off air. I had to reboot my Vision mixer. I had about half a dozen people or more all listening, waiting to listen to me, and I they couldn't hear me. But anyway, I've got it working now, I think. So if anyone can hear, let me know. How's the audio? Just let me know if audio is working. Okay, we're back. Just waiting to see if anyone can let me know that the audio is working. Maybe just in the chat. If you want to just type something into the chat, that would be great. And I can have confirmation that I've fixed all my problems. Can you hear me, guys? Okay, just checking. Audio's working. So we've got a few people watching. So we had a bit of a calamity when I started the live stream. And yeah, it was pretty silent. In fact, you could hear nothing but crickets. Something like this. Yeah, you could hear nothing but crickets. But I'm still waiting for anyone to let me know that the audio is working for them. So if you could just jump in the chat and type a few words, just say, yeah, I can hear you fine. And then I'll get into it. I'll get into 4777 Part 1. I just don't want to talk to a room full of silence. And it would be nice to know that audio is working again. Now, I know there is about a half a minute delay between me broadcasting and you hearing it. So I'm just kind of waiting to see if anyone responds to my chat. Can you hear me? So if you're watching on a device, you might have to... Yep. Yay, Jeff. Woo. Okay. All right. Let's start this whole show again. And I'm nearly a half an hour late, so I'll just extend it a little bit. And sorry for those who are all tuned in on at the correct time at 1 p.m. Australian Standard Daylight Saving Time, or 3 p.m. for you Kiwis. But yeah, now where was I? Okay, I was giving you a little spiel, until I noticed in the chat that no one could hear a word. So let's roll this back. Yeah, it's been an interesting week for me. I've been in China and in central China in Chengdu at the PSEC 2025 conference. I was actually one of the presenters there on this great big stage. It was a little bit exciting. And I was there with the CEO of the World Wildlife Foundation and some other dignitaries from the Global Solar Council. And we were hosted by Tongwei, who make TW solar modules. They very kindly invited me to the event to speak a bit about installing their product. So I have installed a couple of arrays, the earlier versions, the PERC cells, and now the TNC 2.0s on the roof directly above me here in the studio. The new 470 watt all black modules, really great looking. So that was my week. I wanted to give a shout out to all those in Northern Australia who might be affected by Cyclone Fina. It's just passed over Darwin at a Category 3. I believe it's building to a Category 4, but still hanging around the coast of Northern Australia. So it's going to do some damage. So hoping people are safe. It's the biggest cyclone since Cyclone Tracy in 1974 to hit that area. So, yeah, it's a bit of a big deal. And I've actually, for my first time, experienced a cyclone earlier this year in Hainan, which is a island just off the coast of China. It's actually part of China, but it's not mainland. It's opposite Vietnam. We got a Category 5, and it passed right over the hotel where I was staying, which fortunately was a modern concrete-built hotel. So we just barricaded the doors and buckled down, and it sort of knocked down a lot of trees. But we were okay. The city looked pretty bad. Airport was closed for a few days. They had to pick up all the planes. But yeah, cyclones are really phenomenal. So today I'm going to be talking about 4777 Part 1 2024. Now, it has been published, as you would know by the date, for over a year, but New Zealanders haven't been able to use it because New Zealand electricity regulations had to be updated. And they hadn't been updated since, wait for it, 2010. So like 15 years of waiting. So you guys from New Zealand have been using the 2005 edition of 4777 Part 1, which is ridiculously out of date. It was written when there was very little solar connected to the grid. The scope of the only went up to 30 kVA because they thought that was a pretty big system back then. So, I'm very excited that New Zealand now has updated their electricity regs, and therefore 5033 2021, 4777 Part 1 2024 are available for Kiwis. And I guess one of the big news stories for them is that you can now go up to 1,000 volts on domestic systems and 1,500 volts on non-domestic. So that's been something really holding back some of those larger three-phase residential systems, because three-phase inverters really need a high PV input voltage to be efficient, generally over 600 volts. So yeah, now you can get into the sweet spot when you're building a three-phase system. So I've got a bit of a presentation lined up, and I might just throw that up on the screen. But actually, it's a little sweetener for a course I'm running on the 10th and 11th of December. It'll be from 11 till 3 p.m. New Zealand Daylight Saving Time. So it's really aimed at my Kiwi audience, so anyone's welcome to subscribe to it. It is a joint standard with Australia. So, you're welcome to join in, even if you're not in New Zealand. But I think it's the time for New Zealanders to catch up with the latest version of those standards. So I'll be covering 3 standards, and I'll just show you them here. So it's going to be 4777, as I mentioned, Part 1, the latest version, 5033 2020, the latest version, and this is interesting, the battery standard. It's a new standard published in 2019, 5139. Now, there's a curious way that New Zealand regulations work, and I'm sure all the Kiwis know this, but when they do an update, they only update already published standards initially. And that means 5139, which wasn't an update, it's a new standard, didn't get reference to the New Zealand electricity regs directly. Yeah, kind of weird. So another interesting point is that since ASNZS 3000 2018 did get updated, if you read the introduction to it, the normative references include 5139. So how that works? Well, if you are following the requirements of a standard, a normative reference means that to comply with the standard, you need to comply within the scope of the normative references. So logically, if you're following 3000 and installing a battery system, you actually need to comply with 5139. So there you go. Now, I've reached out to WorkSafe New Zealand to see what their view on this is, and I'm still waiting to hear back. I think it's still in the yet to be decided area, but I should point out that they previously said, even before 5139 was published, that because it was not replacing an existing standard and provided best practice guidance on safety for installing battery systems, that even though it can't be required for a record of inspection, it can be used in a court of law. So we'll take that for what it's worth. If things really go pear-shaped, you should probably have followed 5139. There you go. Now I've got people back, not as many as before. I think a few people just gave up on me. Let me know where you're listening to this from. I know where Jeff is, up at lovely Bellingen. So nice to have you on board, Jeff. And some of my usuals probably missed out because of that stutter with the beginning of my show. Anyway, let's dive into 4777 Part 1. Now like I said, I have a few slides here, and I'll just bring them up if I can get myself into gear here. So the standards are joint with Australia, and therefore you are using exactly the same standard that we're using here, and that's great because it means for me as a trainer, I don't have this kind of weird phenomena where I've got to effectively speak two languages. Like when I'm training in Australia, I'm training to the latest. When I'm training in New Zealand, I've got to explain that I can't tell you to comply with the latest, but I try to tell people what some of the best practice information in those is. So the course that I'll be delivering on the 10th and 11th of December, it's 2 4-hour sessions, will be recorded, and it will cover, as I said, these 3 standards. I'll also talk a little bit about the best practice guide, which is to do with batteries, but that's not a standard, that's just a product or quasi-product standard. And they'll be delivered somewhat like this, with some slides, with me, a talking head, and it'll be live so you can chat because it'll be via Zoom. And I'll also take email Q&As for those who can't attend live, because there's often quite a few people drop in for part of the course and then have to leave. So the post-event, I will also provide access to all those recordings of that training session, and there's no limit on how many times you can watch them or how often you can watch them. They'll be effectively YouTube unlisted videos just with a link, and I'll be providing the option for email Q&A post-course. So there you go. That's a little promo. G'day, Craig from the sunniest place in New Zealand, Nelson. Almost sunlight hours. Not the most peak sun hours, but most sun hours. Because basically, the closer you're to the equator, the better it is for peak sun hours. But you get longer sunny days at a slightly more southerly latitude in Nelson. Taranaki, g'day Ryan, and Jason from Brisbane. Wow, we do have a good spread. That's great. So let's start on 4777 Part 1. And what's changed? Well, you always start with the scope to understand if you even need to comply with it. And then we'll talk about some of the general requirements, the connection requirements for inverters, which I should point out are called IES. We've moved away from using the term inverter. We talk about inverter energy systems because there can be more than one inverter and they may be part of a system, i.e. aggregated together. And we'll explain some of the connection requirements, some of the specifics around multi-mode inverters, your favourite topic, more signs and labels, because don't you feel safer the more you put up? No. And some of the documentation requirements. Now, that last one, verification, is actually a requirement of the standard. You need to verify an installation. And so there is Section 8 is a methodology for doing verification. Now, a lot of this stuff, people think, documentation, verification, they're kind of like optional. No, they're all shells. So don't skip over those. All right, so scope is for connecting an inverter energy system at low voltage, i.e. That's over 120 volts DC or 50 volts AC. And then, of course, inverters output is AC, so over 50 volts AC. It does now include connection of electric vehicles, so that's a change. In fact, a very welcome change. One of the exciting things about this standard now is that you can actually have bidirectional inverters that can use the vehicle as a source of energy. And we've spent a lot of time trying to solve all the safety issues around that with this standard. And with any scope, there's usually exclusions. So an exclusion here is for high voltage connection. So if you're doing a solar farm, for instance, and directly connecting to medium or high voltage, then you just need to conform with the DNSP's requirements or the transmission requirements. And if you are installing a UPS system, you need to comply with the UPS standards. So, as I mentioned, the scope is for connection of electrical installations now to the grid, but it, as you'll see in a minute, it also includes standalone systems. The term electrical installations now is used instead of a residence or a building, because electrical installations can be varied in their nature. It also applies to electric vehicles as supply equipment. That means that they can supply, not just be a load, but supply energy back. We're also introducing a bunch of new terminologies to describe the natures of supply. Words like alternative supply, independent supply, etc. And I'll explain those in more detail. It does not, as I mentioned before, apply to UPS systems. They have their own standard. So if you're doing a UPS, which is not providing a back feed to the grid, it's just an uninterruptible power supply, then you're out of scope for 4777 Part 1. Now, I'm going to turn my little face off so we can see a little bit better. Let's talk about supply types. Now, we used to just talk about normal supply and solar supply or inverter supply, but what we've tried to do now is harmonise with AS/NZS 3000 and use the terminologies that are already in 3000. So the ones I've put an asterisk next to are terminologies used in 3000, such as grid, supplementary and alternative. And we've added a couple of extra ones there, independent and substitute. So I'll explain those. It does seem a little bit complicated, but it does actually flow through to your labelling of main switches, for instance, and any documentation. You need to use supply type names correctly. So the supplementary supply means it supplements the grid, and that's what you would consider a normal solar inverter connection without a backup functionality. All it does is, when the grid is available, provide a supplement to the grid to help reduce grid imported energy, or perhaps export it to the grid to assist, or sell energy to the grid. And that nature of supplementary supply is can be used as the label for the main switch, but also you can still use more conventional inverter supply. We're kind of allowing a bit of overlap. Now, actually, when it comes to overlap for New Zealand, I should point out that when the New Zealand electricity regs get updated, or have been updated on the 13th of November this year, you get a 1-year adoption period. That means you can use either the existing standards that were under the older version of New Zealand electricity regs, or you can use the new version. But if you do use the new version of standards, the ones which are now concurrent with Australia, you have to use all parts of it. You can't pick and choose from an old version this clause and the new version another clause. Okay, so you've got to use all of it. Okay, independent supply. What's that about? Well, an independent supply, to state the definition here, is a supply intended to supply the functionality of an electrical installation or part thereof as an islanded operation instead of the grid. Okay, whilst the grid remains connected. So you can turn off the main switch and still provide power to that independent circuits. Normal supply, also known as grid supply, that's pretty self-explanatory. That's the grid coming in. Substitute supply. Now, this is a bit of an odd one. So it's an electrically separated supply with no connection, no neutral, no earth, no phase connection to the grid. It is a complete substitute, and it can only supply a single socket outlet, with a maximum capacity of 15 amps. So it's a pretty narrow definition and pretty unlikely use. But yeah, that's one of the requirements for substitute supply. So someone just came to the door, and moving on. Alternative supply. An alternative supply is one which can be an alternative to the grid, such as when the grid is, in case of interruption of the normal supply, it can maintain the functionality of that electrical installation. Now, I'm just going to skip back a couple of slides to show you those again. So, oops, here we go. So, a alternative supply is what you would think of as a normal backup circuit on a hybrid inverter. So it can provide power to the backup circuit, whereas an independent supply can completely function such as having SP Pro and Fronius in combination. I gave that as an example, where when the grid's not available, the SP Pro becomes a grid-forming inverter system and allows the Fronius inverter to parallel with it and continue to provide a source of energy. And so that's an independent supply. So yeah, those ones are a little bit tricky, the definitions of them, alternative and independent. Okay, just scroll back through. Right, section 2, this is kind of like a general requirements. And as I mentioned, it's for connection to at low voltage to an electrical installation, including EVs, both on and off grid. So right, off grid is included in 4777 Part 1 now. It used to be considered really a grid only standard. Now here is a circuit diagram, schematic of a installation with a solar inverter. Now, well, actually we just call it an IES with an energy source. Now, if you look on the right-hand side of this diagram, energy source, the reason for this as opposed to saying PV is an inverter can be supplied with energy from multiple means, such as wind, hydro, solar, right? They're all energy sources, or even a battery as an energy source. The inverter, of course, now, if it's connected to the utility grid, needs to comply with the safety standard for inverters, 4777 Part 2, 2020. And that standard has been in use in New Zealand for some time because it's actually a product standard and not an installation standard. And of course, you can't even buy inverters compliant to older versions of this product standard. So yeah, they will all have the latest. A little bit of a side note here. I kind of want to branch off, and this Jeff might be able to add some experience to this one. So I probably should have started with this, but for those who haven't been living under a rock and haven't heard that SIG Energy have had an ACCC recall on their 8, 10 and 12 kilowatt single phase inverters because of an overheating of the plug connections, the AC plug. This has been kind of quite dramatic, really, as a lot of inverters have been installed of that capacity. And SIG Energy, to their credit, have responded by saying they'll replace them and they'll provide a $500 fee to installers to go and replace them. But what was the cause? And so this is kind of the one that's a little bit hotly debated. From what I've read and from what SIG Energy has stated with some evidence, is that poor connections have been the cause. And those poor connections are because of incorrect crimping of the ferrules onto the cable that's then inserted into the screw terminal for the AC plug. And that's become a high resistance joint, and then under high powered single phase inverters, up to 12 kilowatts, causing heat and eventually failure. But one of my engineer friends, Ranjit Malawar, he pointed out to me that, and this is where I'm kind of coming back to 4777 Part 2, the 2020 edition introduced a new requirement. Inverters have to have a functionality called low voltage ride-through. Now, what is that? Well, it's to support the grid when the grid's starting to struggle. And so if the voltage on the grid starts to fall, the inverter is required to try and ride through that dip in voltage by increasing its output. And so it's increasing its current output to support the grid and not just isolating, not just islanding. Now, what this means is that if you have a high resistance connection on your AC output, that will cause a voltage drop. The inverter will sense that voltage drop and will try and assist by increasing the power. And ironically, that will accelerate that thermal overload of that high resistant joint. So you could say that in some regards, this problem has become exacerbated by the latest version of 4777 Part 2, where the inverter will try to increase power when there is a dip in voltage. So there you go. Multiple causes for that overheating problem. So there you go. So anyway, back to 4777 Part 2. Jeff just said, yep, had a plug melt 1.5 weeks ago. Just happened to be the day Sig Energy made their communication. Right, there you go, Jeff. Yeah, I believe there's been a few hundred incidents, but there's been something like 12,000 inverters installed, so it is a very small number. So, Jeff, I'm not pointing the finger at you. I'm sure you did a very good job installing it, so maybe there still is some legitimate issues there with that connector. And what they're doing is replacing the inverter with a different type of connector using OTs. It's basically a screw terminal, which is the same as on the three-phase inverters. And Jeff pointed out that there are two versions of the 8, 10 and 12 kilowatt inverters. The original push-fit AC connector was the worst version, and that was the one which Jeff installed, over 50 in total, and they used ferrules. That's right. So the push-fit seem to be the ones that are being replaced. Yeah, good on you, Jeff. I noticed on solar cutters there was a big discussion about what tools you use for crimping your ferrules, and it seemed to be a 50-50 between the two different types of crimping tools. So that was interesting. Be keen to know what sort of crimper you use, Jeff. Hopefully not just a pair of pliers and give them a squish. There you go. All right, back to 4777, and I just realised I increased the transition too far. There we go. So back to this diagram. Now, you might notice that the labels for main switch grid and main switch inverter, which a main switch inverter is the supplementary supply, are in red on a white background. Now, you might think, we now have to go and get new colours for our labels. Not exactly. This is actually from 3000. 3000's requirement is that main switches need to be identified from other circuits in some way. And there's lots of ways of identifying them. For instance, you can do it by distance. You can group them together and have a gap. It's pretty common in New South Wales, I've seen, where to have a half-pole gap between main switches and other circuits that they control. You can do it by labelling. You can do it by colour. So you actually might have a main switch that's got a different tongue coloured, like a red, isolator tongue. So this is just one way of identifying the difference between a main switch and the circuits that it provides. Cool. Jeff just said they're replacing the second version too, but my guess is the first version that was causing issues. Yep, proper crimping on ferrules. Okay, Jeff, that's interesting. I didn't realise there were actually two versions which were using ferrules, a push fit and a screw fit. I didn't know that, so thanks, Jeff. Wow, you've done a lot, 50 installs. Does that mean you've got to go back to 50 of them and change them? Wow, right at the busiest time of the year, when everyone's saying, can I get my new SIG system installed just before the battery rebate reduces on the 1st of January. Yeah, I feel for you. A crazy time. That's what rebates do. Okay, so yeah, just explaining that colour difference on the main switch labels. Okay, here's a slightly more complex one. And Jeff just pointed out that the second version of the AC connector had a screw to capture the AC connector as opposed to a push fit. And yeah, Jeff's not happy. It's a lot. My God, 50 to swap out. Wow. Okay, so other fun recall. I don't know if you've seen the recall in the US of of Tesla Powerwalls. Yeah, that's another big drama. I think that's a bit more serious because they've been actually catching fire the batteries, not just an overheating AC terminal. I think that's what you're really worried about, is something that'll burn your house down. So where are we? This is a schematic showing a main switchboard and then a subboard, and the inverter system is connected to the subboard. So what's different here? Good on you, Jeff. He's grinning and bearing it. He says, I still love SIG. The subboard is got a sub-main isolator, and that sub-main isolator now needs to be labelled main isolator with the indication that it's got a grid source. So that's a change. So main isolator grid, and we've still got our main switches for grid and inverter in red to differentiate them, the labels, from other circuits. Sparks NZ said recalled in New Zealand also. Yeah, I think it's probably going to be a wider recall, but yeah, I'm not surprised. At least you probably haven't got so many to do in New Zealand as in Australia. I think they've, considering that 30+% of all battery systems installed under the rebate have been SIG Energy. There's a fantastic number of them out there, but it is only the 8, 10 and 12 kilowatt single phase units that have been subject to the ACCC recall. Yeah, so what else about this one? That's probably all I wanted to say, just that we've now got a main isolator. It's got to be called main isolator grid on that subboard that's being fed from the main switchboard, which has, that subboard has an inverter system connected to it. Okay, so single phase point of supply. We've now allowed much bigger single phase connections. So an aggregate of single phase inverters shall not exceed 30 kVA or 130 amps. Wow, that's, yeah, there's not many single phase inverters that big, but you could aggregate them. So Jeff might have put in 3 10 kilowatt SIGs, single phase, and paralleled them all together for an awesome single phase system. So yeah, up to 30 kVA. The 5 kilowatt export limit is a guide when you've got a shared low voltage network. Now, a lot of this stuff comes down to the DNSP, or in the case of New Zealand, lines companies' rules. I think New Zealand's got something like 26 lines companies, so it's quite a lot for a small country. But yeah, they all have their slight variations on rules. So even though the standard might say you can go up to 30 kVA on a single phase installation, you still have to get an approval for that. Just another little aside, by the way. I was just noticing on LinkedIn someone comparing the cost of installing solar systems in Europe, in the USA and in Australia. And Australia is about 5 times cheaper for the same size system to install than in the USA. And why can that be? Well, there's a bunch of factors, and things like roof types influence the cost of installation, because our roofs in Australia, tile or tin, are relatively, as in New Zealand, is pretty common, though you do have some of those pressed aluminium roofs, which are a bit scary. But tile and tin is very easy to fix to, whereas your US shingles covered with gravel and a bit of tar paper require special mounting brackets, and that takes longer. But the big one is permitting. Permitting in the US is a nightmare, and it varies with different regulatory areas. So typically permitting can take months to get approved, and there's usually quite a hefty cost for that. So just for the joy of installing solar, you might have to pay your local government authority many thousands of dollars just to have the joy of putting renewable energy on your roof. So that adds to the cost. The other big factor too is experience. The more you do something, the better you get at it. And you know, in Australia, where more than 30% of all the homes have solar installed, solar installers have got very efficient. Everything down to how they set up their trucks and utes, how they disperse the roles within the installation, who does what, and the training of thereof. And so we've got very, very efficient. So, you know, one day, generally you'll see, 6-7 kilowatt system being installed. It's not a multi-day job. One other thing, which is kind of a little bit dubious, and this was noted by the Rocky Mountain Institute when they did a study of Australian installers to see why we're so cheap and so fast, is that we take a bit more risk than the US counterparts. So things like walking on tilts, 2-story roofs without edge protection. Now that is in many states, non-compliance for work safety. So I know in Victoria where I live, it's mandatory to have edge protection when you're working above, I think it's 2 meters or so. But it is flaunted quite often. And I've even had some of my students, well, at least one, fall off a roof. Fortunately, not seriously injured, just a broken ankle, because he was telling me why his assignment was late. He's in hospital with a broken ankle because he fell off a roof. So, yeah, that's one of the reasons that we're so efficient. Got a few more people checking in there. G'day, Day. Nice to hear from you. So, back to 4777 Part 1. I'm actually going fairly slow here because I'm wanting to tell you a few stories as we go, because just talking about standards can be a little bit dull. All right, where are we at now? So I'm blocking too much of that, so let's try and hide my face. Multi-phase point of supply. So we've got a three-phase installation, whereas single-phase inverters without an energy storage port. Now, what on earth is that adding? Basically saying without a battery. A lot of the wording in the standard is very generic. We don't use words battery, energy storage. Okay, so if you've got a single-phase inverter that has no battery attached and a single-phase multi-mode inverter with energy storage port, being for energy storage only, is connected to a multi-phase installation, they shall be connected to the same phases. Okay, that's a very wordy way of saying that you can't put a solar inverter on phase A and then a battery AC coupled inverter on phase B. The storage inverter and the solar inverter need to be on the same phases. So there you go. That's kind of what that means. Sparks and Z says some US states allowing balcony solar. Wonder if that will increase the uptake of solar. For those not familiar with the terminology, by the way, balcony solar is something that it sounds like you have to have a balcony. You don't. It just means that you are plugging into a socket outlet a bidirectional inverter. So whether it's solar only or solar and battery, and then plug into a socket outlet. Now, don't freak out. There's actually some rules around this. Now, this is very popular in Europe. I know in Germany there's over 400,000 approved balcony systems installed, and they have in their VDE, which is their safety standard requirement, for a maximum of 800 watts of power. So you're not injecting kilowatts into that socket outlet, only up to 800 watts. And so it ideally suits something like a small, one or two panel system, because panels are very big these days, can just attach to somewhere where the sun shines. And at fairly northern latitudes like Germany, where you're in the sort of 45 to 55 degrees from the equator, panels that are almost vertical facing south, because remember the sun's in the opposite direction most of the day to us down here in the southern hemisphere, facing south actually work quite well. So hanging panels over your balcony. And it's not just a little clip. There's proper mounting systems for this. Then you've got either microinverters that directly plug into a socket outlet, or a hybrid inverter battery system. I've got a couple behind me actually. Don't know if you can see them on the floor back there. There's some balcony ones just here from Anchor. One of them's got like 4 MPPTs, even though it's only 800 watts output. So you can have panels of different ratings, a mishmash, all connected to the same device. And they've also got an app which allows you to choose when they export. So you can store that energy in your battery and then tell it to export up to 800 watts at certain times of the day. So that's what balcony solar is all about. Why don't we have it in Australia and New Zealand? Well, partly because of 4777 Part 2. 4777 Part 2 and Part 1. Part 1 says you must connect via fixed wiring any IES inverter systems. So plugging into a socket outlet is not fixed wiring. It also has to be a dedicated circuit, so it can't be a circuit that's shared with loads. You can have loads on a inverter supply. And those are all kind of written around the fact that inverters can inject large amounts of power. So you need to ensure that the cable is correctly rated for that amount of power. But with a balcony power system where it is less than your standard 2.5 mil wiring, 800 watts, it's not much current. It's not going to overload that circuit in reverse or or charging. So yeah, they overcome that issue, but our standard hasn't recognised it. Now I know there is quite a bit of pressure actually to consider balcony power for Australia, and we'll see. It was pointed out to me that 30% of Australians rent, and they can't therefore have solar because they're renting, and balcony power would be a way to give renters access to renewable energy. It's probably a similar number in New Zealand. Not sure of those facts, but there you go. Balcony power, very popular. It also means if you're a renter, you take it with you. So it's not like it's on the roof. You could just put it somewhere that you can temporarily mount it, a couple of panels. There you go. Okay, thanks for that, Sparks. And back to, covered that one. Okay, so this is just a little table to explain the limitations on capacity. So with multi-phase installations with imbalanced configurations, it must be less than 50 kVA rating. And then we break it down with inverters with energy storage ports, i.e. batteries, maximum of 5 kVA per phase if they're single phase. Multi-mode inverters with only battery port. Now, what's that? Well, once again, this is kind of how the standards kind of state things in a slightly generic way. An AC coupled battery is effectively a multi-mode inverter with only a battery port. It doesn't have any solar input. Think of Powerwall 2. That's a inverter and a battery in a box, and therefore it's can only AC couple to the installation. And so they're limited to 5 kVA per phase. If you have EV supply equipment capable of reverse power, it's also 5 kVA per phase. Now, this is a really odd one. So what we're talking about here is that the inverter, now be careful here, people often say, I've got an EV charger. What they actually mean is I've got EV supply equipment on the wall, more technically known as EVSEs, EV supply equipment, which is an AC source that I connect to my vehicle, and my vehicle has an inverter inside it that converts that AC to DC to charge the battery. However, it is possible to have a bidirectional inverter in the vehicle. I don't know of any that have this, that can then export power back out from the battery, convert it to AC, and send it back to the supply equipment. Yeah, pretty odd, but there's a big problem. The vehicle itself in Australia and New Zealand, to be able to do this, would have to be 4777 Part 2 approved. So vehicle manufacturers would have to go and get their inverters 4777 Part 2 approved. Probably not going to happen. So we'll come on to EVSEs in a minute and explaining the different modes that you can charge them or connect them. And where you've got an aggregate of multiple IESs, up to 10 kVA per phase. So you've got 2 5 kVA inverters together, a maximum of 10 kVA. So there you go. Now, of course, the caveat is any of this can be overridden by lines companies and DNSPs. So these are just guidelines really in the standard. So for multi-phase inverters greater than 50 kVA, the difference between the aggregate single-phase inverter's apparent power on each phase shall differ no more than 10%. So what that means is you're not putting in a 3 kilowatt inverter and a 10 kilowatt inverter on the same phase. On different phases. They need to be balanced across the phases. So phase balancing is what the intent of this is. Now, New Zealand does have that very peculiar rule where metering is done on a per phase basis. I think it's probably still true. It's only 2 countries in the world that do this, the Czech Republic, or Czechia now, sorry, they changed their name, and Aotearoa in New Zealand. And that means that there's kind of curious benefits of balancing. If you have a phase balanced system, you're actually required to export on phases that you'll not get any financial benefit from. You're not netting the sum of export and import in real time. You're actually getting billed for your export, credited for your export at a small rate and billed for your import at a higher rate at the same moment. so it's not netted. And therefore, it makes sense to actually put in a single-phase inverter on the most heavily loaded phase and maybe even avoid a three-phase configuration. Yeah, it's a bit of an odd one. There might be other solutions for New Zealand, particularly once you add energy storage. You can kind of move the energy around and achieve some other benefits. Okay, so what have we got here? So connection of the IES, as I mentioned, it must be to a dedicated circuit. That's not new. We'll cover the requirements for selection of wiring systems, control and protection, isolation, interface protection. There's a new term. What used to be called secondary protection or grid protection is now referred to as interface protection. Well, what that means is where you interface with the DNSPs or the lines company's equipment, there may be rules around, and there's some default settings in this standard about the maximum size that you can have before you need to have a separate piece of equipment known as interface protection. Now, I know in New Zealand that this is still a bit of a moving target, whether DNSPs or lines companies, I should say, actually require it. Certainly in Auckland, in the Vector area, I know it's well enforced. Once you go over a certain capacity, they'll want a dedicated interface and protection device. I've even heard people say in other jurisdictions it's a don't ask, don't tell arrangement, which seems like you're dodging a bullet, but until they start enforcing it. But the standard does give a much higher start point now for interface protection. What used to be 30 kVA in the old 4777 is now raised to 200 kVA. And that's to acknowledge the fact that inverters are capable of export limiting very effectively, and therefore adding extra equipment to kind of limit export as a special device is not necessary to get to above 200 kVA. We'll also touch on IPSDs, inverter power sharing devices, totally new section, IPSDs. Now, what on earth are these? They're really developed for apartment buildings where they have a common roof, a common inverter system, but they share the energy amongst all the units in that apartment building. And they do that by basically switching the supplementary supply on and off to different apartments. You should see no change in your supply's always got the grid, but whether some of it's coming from renewables at that time or not will be determined by the IPSD's programming. But there are some rules around that, and also the requirements for IPSDs in terms of safety. Okay, connector requirements. So get my face out of the way there for a second. The IES shall be connected either by fixed wiring or by a connector coupling arrangement. Now, what does that mean? Well, most of your sort of domestic inverters these days often have a shrouded male coupler that you connect, and it requires a tool to remove. And so that's an installation coupler. It's not a 3-pin plug, right? And the requirement is that those connectors are of type B. Now, type B meaning that they require a tool to disconnect. Now, we did have, speaking of recalls, a recall from, I think it was GrowWatt actually, because you could actually remove the connector without a tool, and I think you could even expose the terminals so without a tool. So that was a little bit of an oops. So yeah, type B connectors are required. This also means that you can, let's have a look. I'll just come back to this, get my face out of the way for a second. There should be no accessible live parts to at least IP2X when engaging or disengaging. Now, what does that mean? Well, even though you've got a male plug which has the grid supply on the other end of it, even if you try and touch the pins, you can't, because they're shrouded to IP2X. That's a standard test finger. So they're recessed. Now, there has been some failures of this compliance, and I think I've got a picture of one. Where are we? That's not it. There we go, that one there. This is an inspector just pointing out that you can actually touch the pins on this connector with your finger. And so even though it does have a locking mechanism once it's installed, it's still dangerous when it's not connected. So that's not permitted. So there's an example of a Wyland connector on the right here with a locking pin, and it requires a tool. I'm actually not so sure about the one on the left anymore. I don't know if that does have a locking pin, but it's certainly the one on the right does. And therefore, once it's plugged in, it's can't be disconnected without poking a screwdriver into a little hole. Okay, where are we? Installations with engine-driven generating sets. Yeah. The IES shall be connected to the grid side of any generator changeover device. Okay. Now, you might go, oh, hang on, but there's plenty of systems that can actually parallel with another source even when the grid's not available. And what does that mean? Well, there's an exception. It says, except when the engine-driven generating set as the alternative supply, and the IES are appropriately designed to operate in parallel. So I'm just going to use brand names here. So for instance, Selectronic can take a generator as a source, parallel their inverter with it, and as this little picture shows, provide a solar inverter as another source all at the same time. And they can even switch between grid and generating set. So they can have a contactor that can switch between grid and generating set. So when the grid fails, you've got a backup generator and you've got a solar inverter, but they have a reverse power protection feature, so no solar power or battery energy can flow back to the generating set. But if the equipment lacks that functionality, is not specifically designed to work in that way in parallel operation, then you have to connect the generator on the grid side so that when the changeover switch is operated, the generating set is not in parallel with the solar inverter. All right, this is a little kind of explainer which is about cable selection really, and it says that all cables between the IES and any switchboard and all cables between any distribution boards and the main switchboard that carry current from the IES shall have a current carrying capacity not less than the rated current of the IES. Now, I've had it pointed out to me that there are some single-phase inverters that have quite high potential output, but you can export limit them. So, for instance, they might be able to put out 70, 80 amps, but they can be export limited. But that doesn't circumvent this requirement. That means even though you might have set export limiting, you still have to rate the cable for the maximum possible current. The reason for this is export limiting isn't a magic bullet. It isn't, as it sounds, like a hard limit. It's a soft limit. Basically, the inverter's using usually a power meter or a CT upstream to determine how much current is flowing and will ramp down its output to the target value of export limiting. It doesn't do it instantaneously. And so it is possible to get a brief excessive amount of leakage, you could call it, of exported energy before that export limit's reached. Now, when it comes down to billing, it probably doesn't make any difference because when it comes down to billing, it's a momentary event, and so you won't actually see any more sort of export being credited to you, but the cables may well experience it. So if you've got an inverter with a 10 kilowatt output, you need to rate the cables for that. Now, I also wanted to point out that when it comes to cable selection, you've got to be careful here. You might think that you've got a 5 kilowatt export limit and therefore using ASNZS 3008, the standard for cable selection, you might think, oh, well, 5 kilowatts, that's only 21.7 amps. I could probably get away with a bit of 2.5 mil. But because this inverter can deliver 10 kilowatts, you've discovered that you actually got to go up to a 10 mil cable because the derating, and you've got to consider derating as well on top of that. So that's for a wiring enclosed in air, so in conduit. If it's in thermal insulation, it's even worse. So there you go. Just beware of underrating your cables. And we all know what happens when you underrate something, don't we? Things get hot. That's a bit of a problem. Okay, what are we looking at here? Let's get my face out of the way. Voltage rise. Now, New Zealand's starting to experience this. Australia has had this problem for a long time now, which is the more inverter systems connected on a low voltage feeder, typically during the middle of the day, a sunny day, the voltage rises. And that rise can affect the supply requirements from the DNSP or lines company. So they're required to keep voltages to a residence within a certain range. For instance, your neighbour might not have solar, but they may be experiencing high grid volts because everyone else in the street has got solar and exporting at the same time. Now, the way to limit that is to reduce the mountage voltage rise between the output of the inverter and the point of common connection. And the voltage rise is most extreme within the installation, within the electrical installation. So keeping that to less than 2% is the requirement of the standard. How do you determine that? Well, it's really Ohm's law, the size of the cable and the length of the cable. Certainly in Australia, our lines companies, our DNSPs often have a standard online application form, and you have to put in the size of your inverter supply cable, your submain, and your incoming, and those values are consumer mains separate from the submain to the inverter, and so you may have 1% on either side. I think in New South Wales there's even Essential Energy, I think, have 3 sections that you have to meet the requirement for. So yeah, this is all about the reliability of the supply voltage, keeping it within certain bounds. And where it can be a problem is where you've got a rural property. You might have the main switchboard at the front gate, 300 metres of underground going to the house, and that's where the inverter is. Trying to keep the voltage rise down in that circumstance can be very difficult. Sometimes it's better just to end up putting the inverter and the whole PV system out near the front gate. Yeah. Okay. All right, so this is about isolation of the inverter. So for an inverter comprising a pluggable equipment, so this is coming back to that picture I showed earlier on where you've got a AC plug that connects to the inverter that is of type B, i.e. requires a tool to disconnect, then and it's connected by a flexible cord, an installation coupler may be used as the isolation point as an alternative to an adjacent isolating switch. Okay, what does this mean? Well, you don't need an AC isolator right next to your inverter. Your installation coupler is your means of isolating the AC. Given that if you turn off the inverter supply main switch at the switchboard, there's no current flowing, and so unplugging this is not under load and does then provide isolation. So that's a good thing, one less isolator. Okay, interface protection, as I mentioned before, is now the new term for what used to be called secondary protection, or commonly referred to as grid protection or GPUs, grid protection unit. Those are often quite expensive, whereas now we're saying the standard is saying you only require it for systems over 200 kVA. But you will no doubt have to convince your lines company in New Zealand that they will be happy with this, because it will depend on the strength of the grid in your area, whether that's going to be approved or not. Okay, inverters on the same switchboard. Now, where you've got multiple inverters connected to a switchboard, there shall be no more than 2 inverter main switches. Right, so once you get 3 inverters connecting to a switchboard, you actually have to have an aggregation board. That means a board with no loads connected that provide a single sub-main supply to either the main switchboard or a subboard with loads connected. I think I've got a diagram here. Here we go. So here's a system with 3 inverters connected to a subboard at the top, another 3 inverters connected to a subboard below. And that subboard is known as an aggregation board. It aggregates those 3 inverters together. And there's just 3 isolators for each of those inverters. They're not main switches. And then the sub-main from the aggregation board, going back to typically the main switchboard, will be where the main switch inverter is. So there's just one main switch at the main switchboard for all in this case, all the 6 inverters. Now that's been kind of softly applied in Australia for some time now, but now it's in 4777 firmly. And yeah, once you go beyond 2 inverters, aggregation board. All right, there's an example there. So here's 4 inverters and they're all connected to a single main switch to control all 4 of them. Okay, IPSDs, that strange concept of sharing one PV system amongst multiple apartments. This is a Melbourne-based company, Solshare, who make this particular IPSD. I've never actually seen the other brands, so I'm not sure how widely the concept is spread. But it does raise some safety issues that need to be complied with. And for instance, oops, I've got to get my face out the way. You cannot use semiconductor devices as the means of isolating the supplementary supplies. So they need to be able to have an actual switch as well. So there may well be solid state switching, but when you need to isolate your supplementary supplies at the IPSD, they need to be done with air gap isolation. There's an exception for the main switch inverter. It shall be labelled inverter isolator for the input to the IPSD. And for connection of multiple electrical installations shall have a main switch inverter on the load side of the main switch grid for individual electrical installations. So basically, in each apartment, you will have a main switch grid, a main switch inverter, and that inverter supply is coming from the IPSD. So those are some of those requirements. It does take a little bit to get your head around, so yeah, there you go. Okay, I'm going to finish up with talking about EVs. So EVs as an energy source is very exciting. I was recently at the Australian EV Association. I gave a little opening address there, and obviously one of the hottest topics was, when can I use my EV to run my home? Vehicle to home, vehicle to load, vehicle to grid. Well, all the technical obstructions have been removed from standards. So yes, you can. The equipment's available, and those who are familiar with SIG Energy will know that they even make a relatively affordable 12.5 and 25 kilowatt bidirectional fast charging option for their stacks. I got one on my house. It's great. Be able to charge your car at 25 kilowatts, even though I've only got a 10 kilowatt 3-phase inverter. It's using the battery and the solar as part of that DC bus source to be able to charge the car very fast. But the last step is the car manufacturers have to approve the connection bidirectionally. They have to allow the vehicle's battery to be used to supply the load or the grid. Now, we've stated that you can only use mode 3 and 4 in the standard, and let me explain those 2 modes. So here's a little diagram of modes 1 through to 4. Mode 1, I don't think it's even permitted in Australia and New Zealand, which is just a plug directly to your car with no fault protection. So pretty much all those chargers that come with your vehicle, I'm using the word charger loosely because they're EVSEs, is actually got a little brick in the middle, and that brick provides fault protection to that cable, and it may well have a plug or a tethered cable to your device on the wall, your EVSE. So that's mode 2. Mode 3 is where you've got an AC source and you are providing AC, usually single phase or 3-phase, to your vehicle. And the vehicle has then got a built-in inverter that converts it to DC to charge your battery. And mode 4 is where you're supplying DC using Type 2 CCS plug with the extra pins for connecting to the battery directly. So mode 4. So we're only allowing modes 3 and mode 4 for bidirectional. And that's because from a safety perspective, mode 2 is not appropriate. You could be unplugging that and have a live male pin on the end. Not a good thing. But so only mode 3 and mode 4. And mode 3 is pretty unlikely to be used because that means the car has to have a 4777 Part 2 approved inverter inbuilt. Whereas mode 4, the car is just a battery effectively. And the mode 4 supply equipment is the device that converts and is compliant with the grid standard 4777 Part 2. I think I mentioned this right at the beginning that we can now go to 1,000 volts. It's probably a good note to finish on for domestic systems. So it means much longer strings. That really suits some larger roofs where you can just very simply run panels and run them in series. It also is great for 3-phase inverters. And even though 5033 in Australia was updated back in 2021 to allow 1,000 volts on domestic installations, we were stuck by the fact that the old 4777 Part 1 didn't allow it, the 2016 edition. So we had to wait for both standards to be updated. Lucky New Zealand, you get both at the same time. You get 5033 2021 and 4777 Part 1 2024, both allowing 1,000 volts for domestic or residential installations and up to 1,500 volts for non-domestic. So that's really awesome. Well, thank you everyone for today. I'm sorry it was a really cranky sort of start to this event, to my Toolbox Tech Talk with my sound not working. And it turned out that I just had to reboot my Vision Mixer. Isn't that always the first thing you should do? Just reboot and try again. But all good. So anyway, hope to see you all next week. And we'll be talking about the battery standard 5139 and some more of the peculiarities of that standard. So thanks once again, everyone, for watching. And hope to catch you next week with audio from the go. No more of this fluffing around. Okay, thanks.